So good morning. I think it's not really worth waiting longer. I'm very glad to see you in this session after yesterday's terrific closing event. My name is Baiba Kaskina. I work for TERENA and I'm going to chair this recent results session. The goal of this session is to allow members of the community to present results of their projects that are currently running. So the things we will hear today are very recent. If you look in your program, there are 4 speakers for this session. Unfortunately, the last one couldn't make it to Poznan, and it was not also possible to set up a video conference, so we will have only 3 speakers. The first speaker, Prasad Kalim, is currently in the US. It's middle of the night in the US, so be gentle to him. Prasad is working in the University of Ohio for ORNet, and he's going to talk about towards an analytic model for characterizing behavior of high-speed video voice over IP applications. And now I hand over to Prasad. He's seeing slides, but he will hear you if we have questions, so don't hesitate to ask. So please, Prasad.
Thanks, Baiba. I hope everybody can hear me. I'm just waiting for the slides.
Slides are coming.
Okay, thanks.
Here we are.
All right, thank you. So can we go to the first slide, please? So today I'll be talking mostly the points that are on the slide there, a little bit of motivations and what we're trying to study in our experiments. And to get you started on what we're doing, a little terminology about the system itself in terms of the devices, the network issues, and what actually are we measuring from the system. So we're actually measuring end user perception, which is basically what the human factor is about. We'll talk about a little bit about our test bed that we've set up. We've done some experiments, collected some traces on a LAN and on the internet between different sites. So I'll actually give an overview of the test bed and what kind of results we actually collected. And finally, how we're using these results to build an analytical model. And like I just mentioned, just like Baiba mentioned, this is work in progress. So the results are pretty, in a little premature state, and hopefully over time we will have a better picture as to what we are actually trying to find. So next slide, please. So basically the motivation is video conferencing. So we've already seen a lot of progress in this area in the last few years, and there is a lot of interest and push towards more high bandwidth applications which require voice and video over the internet. And some of the more compelling applications that are coming up are the MPEG-based video, IPTV, and the many other applications that are still being accepted in communities but are already taken form in some shape or the other. So there are all these high bandwidth video and voice applications that are going to be used on the internet in the future. And these applications have high resolutions, so they basically put out a lot of data on the network, and they require real-time handling, and also they need to be able to have good access and good user controls for end users to use the application whatever way they want to use. So there's a lot of real-time aspects to the system that we need to study about. And before we can actually build a good system, we need to understand where the problems are or where the bottlenecks are. And that's what we're trying to find and characterize, so we could actually tell what are the weak points that we want to address, so that ultimately what we're trying to get is impress the end user to use the application. So let him do whatever he does without any problems. So we would like to find those bottlenecks and somehow put them into a characteristic form so people can easily identify, go about fixing. So what parameter fixes what problems and things of that sort. And the last point, basically, where it says that we need to actually look at the performance in terms of how the end user actually perceives the quality, because the video and voice systems are pretty subjective. So we need to look at the end user. Can we go to the next slide, please? And this is a brief overview of what our study goals right now are. We actually would like to look at more streams and data which are above the 768 kilobits per second encoding rates. But we generally feel that it's the same even for lesser speeds also. And people have actually studied the lesser speeds for a long time, and it's only recently that people have started looking at higher speeds and what the issues are with those. The issues are pretty much the same, but maybe we need to look at different things when we go at higher speeds, and that's what we're investigating. And the first bullet, as it says, we're trying to understand the device factors. The device factors, basically what we mean are basically the different compression schemes. There are buffering schemes. There are a lot of advances in packet loss concealment schemes. And they are all being implemented in applications today. And they are actually performing much better. And so or sometimes they may not in some situations. So we would like to see how these device factors affect the overall performance. And the second bullet that says evaluating how network factors actually degrade the stream. And this is pretty much what we already know, that delay, packet loss, reordering, things like these, and how they actually affect the streams. We all are aware of it, but and some people have tried to quantify what bounds of these metrics actually affect the end user perception and things like that. But we would like to study in much more detail as to what these parameters actually mean in terms of bottlenecks. And the last bullet is basically what I explained, that we would like to quantify everything, all the bottlenecks, all the issues of the system, and see how it finally affects the end user perception of the video and voice. The end user is the one who's going to actually finally determine what the performance of the system is. And if we go to the next slide, please. So this is sort of a system view of how we are looking at this VVOIP system. And I apologize for the busy slide. There are a lot of terms and terminologies and information on the slide, but it's sort of comprehensive that this slide presents most of how we want to look at the system. So if you could bear with me and follow me as I explain. So you can see from the left side that you have basically some sort of audiovisual content, which could be anything from a video conference just like this to some streaming media event where you're watching sports or something on HDTV, which is being streamed live on the internet. So it could be any kind of information that has different temporal characteristics, and it basically transforms into some sort of discrete pictures, which can be characterized by some sort of frame rate, some sort of resolution, and some sort of quality factors. You can see FR, R, and Q, and things like those. So that's basically the input to the system. And you can see that it's characterized by BS, which basically, if you can go to the right down in the slide, you can see an expression for BS, which basically, again, it's bits per second. It's the bandwidth, what's being actually injected into the system. And then it goes through the compression process. And what we get once we compress the data is basically a stream with some sort of interpacket distributions. And we call that IN as the interpacket distribution, and WN, which is basically different packet sizes. So the data basically gets chopped into different packet sizes to be sent on IP, and we have sort of a mean and sort of quartile characterization of those parameters, which are basically EIN, EWN, QIN, QWN. And so if you go to the middle part of the slide, you can actually see the network part, which basically is characterized by the delay and jitter. And of course, there's loss. And we've sort of inherently associated loss into jitter. It makes our modeling easy. A little talk about it later in the talk. And finally, you can see at the receiving point, once we receive all the packets that arrive, there is a further deterioration in the inter-packet jitter, and there is issues with reordering, and there's a terminology there for that, which is basically the buffering. And then before actually decoding, we actually have all these packet de-jitter buffers and concealment schemes, which actually is not shown in this slide, but it happens, and then you have the decoding, and then you finally, what you get on the end user side is basically the QMOS, which is basically what a mean opinion score is. A mean opinion score is basically a subjective way of saying how good the voice or video is on a scale of 1 to 5. So if somebody were to rank the quality, he would pick a number anywhere from 1 to 5. So we want to actually have our model represent all the bottlenecks in the system, all the parameters in the system as an ultimate QMOS value that basically characterizes how good the system is performing. And people have actually done this in E-model, PESQ. There are a lot of models out there already, and we would like to basically enhance on those principles, but we would still want to look at the system the way we've looked at it in the past. Next slide, please. So this is just a little more clear picture of how the inter-packet distribution is. And this is basically where our real interest is at looking at when we actually analyze the traces, as I'll explain later. Next slide, please. And now I'll talk a little bit about our testbed, what kind of traces we've collected, between what sites and what configurations we use for the testing. And this was pretty much typical what you would expect if you think what we'll be doing, that we have different kinds of clients, and they are all connected. In the LAN testbed, of course, it's isolated, that there's not much cross traffic going on, but we have a Tandberg system, we have a Polycom system, some desktop systems, and a typical TCP dump to basically capture the traces. And I'll actually talk about what exact tests we ran. It's in another slide later on. So can we go to the next slide, please? So that's the internet testbed. We have basically we have collected traces between Ohio, HIANET, and the Russian public network. And in each case, we have collected traces and a lot of measurement data, network measurement data between the paths. So can we go to the next slide, please? So this basically summarizes what is the sort of data we've been collecting. We've collected different dialing speed traces, and we are aware that we can't basically cover all the possible codecs and endpoints out there, but we've taken a representative set, and the traces actually are on network paths which are, like I've shown in the slide, between Ornet, HIANET, and Russian public network. And we've characterized these links with different sort of network information, and these are tools that people popularly use: ping, the H.323 beacon, iPerf, path ping. And it's just to get an idea how the network performance is in the context of where we collected and when we collected the traces. And a summary of how the link performance is shown in the bullets there. We could see that the link between Ornet, HIANET is generally very good, and MOS above 4 is considered to be very good, and in our case is 4.33, which basically signifies pretty good MOS, and that MOS result is from the H.323 beacon test. And pretty low levels of jitter and pretty low levels of loss versus the link between Russia and Ornet and HIANET. And so basically these two links give us a good comparison of what a good performance and what a bad network performance is. So it gives us a nice comparison trace sets. And what we've been doing is we've collected these traces, and we're analyzing these traces using the E3L RTP analysis module. And what we could actually find as data from this module is basically the inter-packet jitter, like I said, at the sender and receiver sides, IN, WN issues. So we actually collect bidirectional traces. We are actually able to look at IN, WN from both sides. And for the same traces, we're able to look at loss and reordering. And the next slide, basically, next few slides will actually explain how we are actually decoding the traces and how we are actually collecting the data. So can we go to the next slide, please? So many people might know this, but for people for whom it's of interest as to how we actually collected the trace and how we are actually analyzing this. So E3L is pretty standard application. People use it all the time. If you're a network engineer, you've definitely used it. And so we actually are looking at traces from both directions. And what we do is we basically decode the streams as RTP streams. So if you just load the trace in E3L, it's pretty much UDP streams. So we basically decode them as RTP. So we were actually able to tell which are the video streams, which are the audio streams. And then we basically separate the streams for each direction in terms of audio and video. And we can actually import these stream information into a tab delimited CSV file. And we're able to do a lot of analysis on the data. And if you're curious and play around with the tool, you can actually see, you can actually generate a waveform of the conversation. And pretty much works only for G711, but you will be able to get the waveforms on both ends. And if you were to use a PESQ program, which requires both input and output audio files, you could actually use the E3L RTP analysis module to feed the files to the PESQ program. And for people who don't know what the PESQ is, it's basically, again, an automated program that can actually look at network traces and actually figure out a MOS score, which is basically 1 to 5, like I said before, which basically represents how good the path or how good the video or audio is going to perform on that path. Next slide, please. So the next 2-3 slides are basically screenshots of how the the RTP analysis module, how we use it to get our data. So this basically shows how a typical stream after being decoded as an RTP stream looks like. So we are looking now at a H.263 payload stream there. Next slide, please. And once you decode the streams and you try to look at what are the streams, you can actually see there are 4 streams, 2 audio, 2 video. And 1 audio, 1 video corresponds to the forward direction, the other corresponds to the backward direction. So we basically study both the directions, so we can actually get a bidirectional information about the path. Next slide, please. And how we are actually looking at packet loss and reordering is basically E3L analysis module basically has a nice feature that when you analyze the trace, it could actually go and apply what's in the RFC 1889. Excuse me. RFC 1889 to see what packets are in sequence and out of sequence, and you can actually see 2 consecutive packets will look like they are basically it could be 2 packet losses, one next to each other, or it could actually be a reordering, and you can look at the sequence numbers and things like that to basically see where the loss and where the reordering is happening. Next slide, please. And you could actually import the data also. So once you get this data, you can actually see you have different packet sequence numbers, different packet size information, interpacket delay, interpacket jitter. And we've not understood what the interpacket delay is pretty much, but what we found useful is the interpacket jitter. And you can actually see there's a timestamp and also issue about if there's a reordering or a loss. Next slide, please. And these couple of slides are basically showing us the performance of the traces, and you can actually look these up in the paper also as to more detailed descriptions. But the table above basically summarizes the E values and the quartile values for the packet size distribution, interpacket jitter for the different streams at different resolutions at different encoding rates. Next slide, please. And the previous one I think was for 384, and this is for 1920. And we actually have looked at this in different packet size ratings, and basically we have probability distributions and things like that to look at what's the characteristic of the data. And next slide, please. what we're trying to get to is basically is summarized in this slide. So, like I said, so we are looking at mainly J and I. And if you can recollect what it was from the previous, the I is basically the interpacket characteristics of the data on both sides of the traces. And J is basically the network trace. And what the equation is basically trying to find is you can, in any case, you can get only a maximal value of QMOS. And in terms of E model and things like that, even though you have a scale of 1 to 5, if you actually run a model due to some system considerations, you can only go up to 4.41, even though 5 is absolute. So imagining that there is no problems and you got the best performance, so that's basically what the Q ideal is about. And it will not necessarily be 4.41 for any system. It can again depend upon what kind of codec, what kind of endpoint, what kind of setting that we're trying to do. Are we doing a desktop system, or are we using an appliance system? Are we using what resolution? So all those will actually determine what the Q ideal value will be. And there are two parameters that are being subtracted and one which is being added. So what the first subtraction, the alpha j, is basically trying to characterize is the degradation of the MOS value due to network factors. And as you can see, j is basically a combination of interpacket delay, which is basically what jitter is, and packet loss, which we believe is sort of tied in because loss happens both at the network due to variances and also at the djitter buffer. So it is sort of easier to characterize the whole network factor in terms of delay or loss just in terms of J, which is found to be the most predominantly the factor that affects video in terms of the network. So, so that's basically what the minus alpha j is about. Minus beta j, beta I is basically about the device issues. So when you encode or decode and things like that. So the interpacket jitter distribution is basically what we are looking at. So once it's degraded, so there's already some sort of spacing, like I showed in the previous one of the slides before the diagram. The spacing is affected by the device factor, and that actually has a great impact on the QMOS value. So how you quantify that is basically by the beta I term. And finally, we have the gamma ji, and that's basically accounting for some of the good things we have on the receiver side. So it's basically the djitter buffer or the packet loss concealment schemes. All these actually improve the quality. They actually, some sort of reorganization of the data happens, and so you're actually seeing an improvement in the performance finally. So there's a degradation from the network and the device factors, but there's an improvement again by these schemes at the end, which actually can enhance or increase the QMOS value. So this is a very broad equation. We have much more depth for what we're trying to say there, but it'll be too much detail to explain in this talk. But I guess I was able to present a general philosophy of how we're trying to characterize these parameters and how we're trying to model this system. Next slide, please. And this is basically how the model looks to us at this point of time, that we would like to have a surface of the QMOS as a function, 3D function of J and I, J being the network jitter and I being the interpacket jitter due to the device factors. And as you can see, with the increase, there is a decrease in QMOS for both I and J values. But the surface is going to basically determine what the quality is going to be on a link. And this is going to be very, very link specific and also device specific. So this is not any generic one-all curve, but this is basically a representative curve. And for pretty much different, any given endpoint system or the network system, we will find a curve which is similar to this, but the surface might have very interesting variations. And that's pretty much where we were trying to find what surface best characterizes what application at what encoding rate or network issue, and how it best actually represents end user perception, which is the QMOS. Next slide, please. So that's the end of my presentation. And I think I took 25 minutes, so if you have any questions, I think we have about 5 minutes for questions.
Yep, questions please. No questions? Then thank you, Parsad, for the presentation. You probably hear only me clapping, but there are more people in the audience. All right, and then we move to our next presentation. Presenter is Saverio Nicolini, and now Saverio is working for NIC, but he's been involved in the TERENA activities for quite some time. Maybe you know him from the Voice over IP cookbook, maybe from some other activities. In NIC he's working also with other issues, but he's still in Voice over IP world, and I think we are all very glad for that, because now his presentation is towards Ambiguous IP Telephony deployment, state-of-the-art, challenges and recommendations. So, Saverio.
Yes. Yes. Okay. So, yeah, should be okay. Yeah. Or maybe I just use for just use this other one. Okay. It's better if I use this one, so you can hear me better. So yeah, thank Baiba for the kind introduction. Basically, what I'm going to tell you about is this recommendation towards ubiquitous IP telephony deployment. Yeah, just to give you some background about what this talk is about. As you have noticed also in this conference and the presentation before, inside the researchers community there is much raising interest about IP telephony and its deployment. And this is demonstrated by a lot of efforts in this area. So as Baiba said, I've been involved in the TERENA activities for some time. I've been one of the authors of the TERENA IP telephony cookbook, who giving recommendation on how to set up IP telephony deployments. And currently there is the TERENA task force on voice, video and collaboration, which is also dealing with some of these aspects and many more. There is also the Internet2SIP.edu deployment, which is a worldwide deployment with a lot of users that are using basically SIP and IP telephony based services and are trying to deploy more. And there are many, many other deployments that I'm not here to cite because it would take too long. So the question that I was trying to answer, and I don't know if I can answer alone, is if VoIP and in general IP telephony technologies has reached the level of maturity that justifies the introduction in the production network of the National Research Network. As we have seen, SIP.edu is a nice application, is a nice example that those kind of things can work and can scale, but we need something more to link all the national research institutions, in my opinion. So I will try to show you what's the state of the art at the moment, what are the challenges, and what are my personal recommendations in order to build such an infrastructure. So, as I was saying, there is the TERENA task force on voice, video and collaboration, and we are deploying and developing a survey on IP telephony deployments. So basically, this is the NRNs are going to distribute these surveys in order to collect experiences on all the deployments that are ongoing work in several universities and national research networks. Well, you can ask why this, because basically there is a need to understand what's the real state of the art. From what I've seen, there are many, many differences, and especially across USA and Europe. Basically, Internet2SIP.edu deployment is focused basically on email identities. You may have seen this nice SIP.edu presentation where they claim that Bob Bell didn't say a number when he wanted to call someone. Well, European deployments are looking also to numbers, are not only focusing on email identities, because they're exploring also the possibilities to integrate other protocols like INUM protocol inside the IP telephony deployments to actually dial also numbers. This is what the global dialing scheme of all the NRNs, and I think also it is thanks to this global dialing scheme that we've been looking at the presentation before. So basically, I just want to say, if you are interested in those kind of things, you should participate to the task force on voice, video, and collaboration. And there is a face-to-face meeting today after the conference. If you haven't registered, it's bad. So just to give you an overview on the state of the art, I'm not now talking about only video conferencing. I'm talking about IP telephony deployment, so such a sort of more integrated deployment. And what I foresee and what I see the effort of the actors in the area is that we are moving to SIP. The testing is all based on SIP because HT23 has no more deployment anymore. It's stable, is on the production network, but the future is going towards SIP. So HT23 is mainly related to the global dialing scheme of the NRNs, and integration with PSTN is not ubiquitous in the sense that there are problems in integrating the global dialing scheme with a common PSTN numbering, and you should use also prefixes, and not all the NRNs are willing to do that, to let the user, allow the user to call also PSTN numbers. There is an example at SARFNet offices, they can do this, but I'm not aware of many other deployments where NRNs allow the users to make outbound call to PSTN because of accounting issues, billing issues, and a lot of. So basically, so far there is no solution to integrate SIP and H323 and exploit what we have really good in the H323 world, which are the multi-point conferencing unit, like 20 user, 40 user multi-point conferencing unit that make us able to really do a distributed and ubiquitous video conference. And we are working on TERENA task force on voice, video, and collaboration is working on that. And what I've seen is there is a massive usage of good open source or free software, like the SIP Express router, the Asterisk software, and also the Extend Lite, Extend clients. This is really good open source software, really flexible, that should be used because it's also, it's okay? Okay. Because it's also easy to use, easy to configure, and there are good documentation about it. So the challenges which I see towards the reaching of such a ubiquitous IP telephony deployment is that there are some limitations. Right now, there is, the network administrator are basically scared of adopting SRV records in DNS, and this limits, of course, the integration of email and VoIP identities. Of course, ENAM, as you can speak with your legal administrator in your network, it's still a problem, like who should administrate it, who should delegate the numbers to the other institution, how to do that, if there is a legal framework beyond that. And this is, as I was talking also with Egon from SurfNet, he said this is a layer 9 problem, like it's a layer over the user that you cannot really control that. So there is definitely a need for more interoperability tests. I was using my SIP deployment at NEC, and I was trying to call a call center. I was successfully connected with this, but I had problem when they parked my call and they tried to pick up again. So basically my gateway crashed. So we also need to understand where are the problems when interoperating among different deployments and among different architectures like PSTN also. And one of the main problem I foresee is that really network layer issues are almost ignored right nowadays. So IP telephony is not ubiquitously working with the net and firewalls. Really only a small number of institutions have implemented the NAT and firewall traversal methods. This is something that really limits, in my opinion, the ubiquitous deployment. Because you can see, for example, the SIP.edu deployment, they are doing everything on top of public IP addresses. When you have to be mobile, to be ubiquitous all over the world, and you are facing like an hotspot, or you are facing your ADSL connection with an STNAT in between, then your IP telephony client is not going to work. So if your institution that does not implement these kind of methods does not allow you to be so ubiquitous as you would like to be. And just a small snapshot on security issues that, in my opinion, are out there, so are about to come, like spam over internet telephony. There's currently a researcher working on this. I'm personally also working on this, and also denial of service attack. As soon as your IP telephony deployment reach a certain value, you can bet that people is going to attack it, because there is a value behind it. So just to give you some recommendation, which are my personal opinion, you can disagree, and I would be happy to listen question on this. I just suggest the adoption of SRV records in DNS. So basically, if a user, let me use this nice pen we received yesterday. If a user is reachable, for example, at his mail address, at mail to user at domain, whatever, and is reachable using his SIP identity at user at sipproxy.domain, whatever, again, you can use SRV records to reach him at the same address, just changing the prefix. So, and you don't even change the prefix, because the application is changing it for you. So basically, if you send in an email, you send it Baiba at TERENA. If you want to contact Baiba using video conferencing, you contact using Baiba at TERENA. So you don't have to remember thousands and thousands of identities. Basically, just suggest your network administrator to configure a simple entry in your DNS. This is just a way of differentiate, so to integrate an identity and to differentiate the machine from the service that is providing. Also, enum can make your SIP user reachable at their telephone number. Once you have only one email identities, one uniform resource identifier identities, you can even afford to give the other people also a number, because they don't have to remember 4 uniform resource identifier of yours, so they can remember one mail address style and one number. So you can use enum to map your telephone number to your user, like using SIP, like as I said here. And this is done using NAPTR records. So I know this is not the golden solution. This is not perfect. This is not going to work everywhere, and it's a problem. But it's just one number to remember, and in my opinion, is really well suited to small, medium deployment. I still have to see a viable solution for large deployments, but this is something that has to come, because... Okay, as I was saying, let's come to the other topic of my talk, that is network layer and security of IP telephony. Basically, as I said, your institution that has IP telephony deployments most probably are not implementing IP telephony on top, behind the NAT and firewalls, because either they just don't care, or they are maybe trying not to deal with these issues, because sometimes are too complicated. But I know they are testing them. So, in my opinion, NAT and firewalls are security devices because they are doing, a NAT is also doing a topology hiding, and the firewall is, of course, a security device. And they are growing and growing. If you have a DSL connection at home, if you have hotspots, they are using NATs, they are using firewalls. So if you want to use your IP telephony client over there, there has to be an implementation that allows you to do this. Just to give you some example, what we did at NEC in Germany, that was basically what I was doing in Switzerland working before, it's having a network with public internet and the router with a firewall on it. Then you have a demilitarized zone with some server in it. You just open some pinholes to those servers. And then you have a NAT with an internal network, which is based on private IP addresses. Well, just to give you an idea, how should you place your IP telephony equipment over there? This is just a suggestion. You can do for sure better. But I'm just suggesting to put the clients on the private internal network behind the NAT. And then you have the servers. Maybe I do it like this. Okay, you have the servers, like the SIP server and the gateway in the demilitarized zone. So you can, if you want, open pinholes to those servers without too much risk, and entering the demilitarized zone, you are still monitored. So basically, what we are employing, it's open source software, it's SIP Express router software, it's an asterisk gateway, and then if you want to have mobile user, they just connect from the internet. But if you provide them a mean to connect to your institution using NAT and file traversal method, they are able to connect. Otherwise, they are just filtered on the router, and they cannot connect at all. So you just to show you, there are problems with NAT and firewalls about the SIP signaling and the media signaling. And I just reported here, you may be aware of that SIP signaling is basically done peer-to-peer, and we have problem because SIP is application level, so basically the exchange of the ports is negotiated inside the protocol. And this is not something that your NAT and your firewall do care about. It's just they are ignoring it. They are just filtering whatever, and they are understanding only IP addresses and the filters you configure on it. Also for the media. The media is a strange thing because you have RTP traffic flowing, and then you have also the RTCP control protocol, which is basically going on RTP port +1. But this +1 is really noisy in the sense that it doesn't pass your firewall or your NAT, because it's simply, if the call is initiated from outside, it's not going to enter because your firewall or your NAT has no association of such flow. And then there are also other tricky things like timeouts that are configurable, and silent suppression doesn't help in this. So, once again, needs of implementing NAT and firewall traversal methods. This is my opinion. Even if you don't have NAT and firewall in your institution, which is your choice, you may allow people to use your IP telephony deployments where they are mobile, because it's most probably that they are going to find a NAT or a firewall during their trip. And if you're traveling a lot, you would be happy to have a NAT and firewall traversal method, because otherwise you are not able to call home, for example. So NAT and firewall traversal method, STAN, simple traversal of UDP over NATs, is an RFC standardized by ATF. There is an open source software available on Vocal, on the Vovida site. You can use it. It's almost well done. It doesn't crash anymore. No, it's easy to use. It's easy to implement. There are a couple of clients, like X-Lite clients, like Xixel Wi-Fi phones, like Hitachi Wi-Fi phone, that has this kind of STAN client to connect to it, and they are able to traverse it. Then there is traversal of UDP relay using NATs. This is TARN. It's still at the draft level, and there are not really open source implementation of this. And yeah, it's kind of relay, but it's about to come like ICE, this ICE protocol. It's also a kind of draft in the IETF still, and it's not yet mature to be implemented. But there is always this back-to-back user agent that it's basically still a good solution to implement. I just wanted to say that all these solutions require user agent to support symmetric signaling and media. So if you want to buy something, if you want to test something, it's better that you have symmetric signaling and media enabled on your client. Stan, just how it works, a Stan client sends out a couple of probes to a Stan server. The Stan server looks at those probes, replies to the NAT, to the client, and trying to understand how the NAT is working, so what type of NAT you have in between, and telling the client, just modify your SIP messages in order to exit your NAT and to be reachable from outside. It's a nice solution. Unfortunately, it's not perfect, as all the solutions, and it's not working with symmetric NATs, which are the nastier NATs available nowadays, and are used by most corporate environments, like mine now. So, yeah, but it's still something to begin with, and you can always combine a couple of NAT traversal methods. I will show you how we did it. And all you have to do is install a Stan daemon server on a machine that you have on the public internet, or you have on the, as I said, or you can have a machine like a Stan server in the demilitarized zone, and you can open pinholes to the machine. Also, a solution to firewall traversal, I wanted to cite them just open pinholes statically. It's a security risk, but sometimes you cannot avoid it because you cannot modify all the firewalls to be SIP aware. If you have tons of firewall in your network, you don't want to change them all. So you just can start opening some pinholes, which is still better than opening all the network. There are stateful firewall, but still require some changing in the firewall. So what I basically propose is to start with a combination of Stan and a proxy solution, like open pinholes just to dedicated host in the demilitarized zone, and using a kind of proxy that is able to modify the signaling when you are not able to traverse using standard methods. So, as I said, you can see here the deployment, and you can add some nice things like co-located with the SIP server. You can add a back-to-back user agent, which is relaying your RTP proxy when you are not able to traverse the NAT. And also co-located, you can have also a Stan server, which is able to let you understand what kind of NAT. Of course, you have to open pinholes to those machines. Just one machine, if you are implementing everything on one Linux machine, it's what we are doing, for example. It's not a case that I put all together. And then you open pinholes also to your gateway, where you should have a little bit more of administrative checking, because you don't want that people use your gateway to call everybody outside there. Yeah, just to conclude, because I think I was faster than thought. Just to give you a short overview, what could be the security risk of SIP and IP telephony, I just reported here some needs that are about to come. I don't suggest to implement them already now, because it's, maybe too early to implement them, because stable solutions are not out there. But if you care for secure implementation, you may care for the security of your voice, the security of your communication, and what you are saying on the network. So you may want to encrypt your traffic. But from one side, encryption on the traffic, it's a good thing. From another side, it adds a level of complexity, because if the SIP signaling, it's a layer application, it's a layer 7, it's application level, and NAT and firewall do have problem with this kind of implementation. They will have even more problem if you encrypt your traffic. So there is, again, the need of using some traversal methods and to let someone in the network to help you. And then the encryption can be done either at SIP signaling level in order to avoid that people just discover your network and discover where your server are. And you can do also media encryption with secure RTP. There is a nice application developed, I think, at KTH in Sweden. No, it's in Sweden. It's called Minisip, and it does implement secure RTP. You can use also this SIP application on a nice PDA. It's called Mini because it's quite small. And of course, there are, to prevent also spam over internet telephony, there has to be a method to assert a good identity. So you know who is calling you. So then using like white and black list, you can also already solve a lot of the problem. There are reported some methods here, and then there are also denial of service and intrusion attack. SIP signaling and media transport is really, really, really easy to attack. You can, just to give you an example, you can just eavesdrop the connection, inject the traffic, and play out whatever message you want to the user if you manage to be in the middle. This kind of method of man-in-the-middle attacks are really easy to do. It's not difficult to do DNS modification in order to be in the middle. And then you attack the network. So there should be also, still in research phase, but it's something to think about. And then, of course, spam, it's still a research topic, and publications are about to come. Just 2 workshops on the topic are right now out there. Yeah, just to conclude, thanks also to Switch National Research Networks for ideas and some material about this paper. They made a nice SIP Info Day workshop in January, and it helped a lot also to understand also a lot of the features out there.
So, questions? Yes, up there. How do we do with the microphone? Oh, there is one.
If you want larger deployments of SIP, you have to deploy at the residential level. Do you have any ideas how that would be done?
If I understood well your question, you are talking about residential level deployments.
Exactly.
Yeah, basically what I've seen is that this kind of SIP proxy are able to route a lot of calls without no problem. Basically, you can have just redundant SIP express router proxies just doing a load balancing on it, but maybe for a lot of deployments you need only one of this SIP express router. Then at residential level, it's just that you have to connect to your operator or like your SIP provider, register to it, and you are available to call it. Either you, in the sense that SIP is scaling as internet, so as scaling with the DNS. So I don't see really much problems in deploying it at residential level as soon as you have implemented NAT and firewall traversal methods. Because it's most probably that at residential level you will have a NAT in between. The classification of NATs reported in the RFC of STAN reports 4 types of NATs. Only one of these is not, it is not possible to pass only one of these using the STAN RFC implementation. This is the symmetric NAT. If we are talking about the symmetric NATs, then it could be a problem of scalability in the sense that you should have more back-to-back user agent to support all your RTP connections. But as long as you don't have this type of NATs, I am pretty sure that also residential level implementations scale. Or maybe I misunderstood what was the...
The question is, most of the ISP providers doesn't support proxies, the SIP proxies, basically. So you need another provider to support usually.
Yeah, I was thinking of, like, National Research Network could provide to the research community such an infrastructure. This is what I think they could do. They could implement a proxy at their level, and they could also delegate some domains to the other institution. Like the more advanced institution that have a good infrastructure, they can implement their own SIP proxy as long as they are able to maintain it and to configure it. Otherwise, you just, if you want just to be SIP reachable, which it doesn't mean that you have a connection to the PSTN, you just connect using free world dial-up or VoNage.
Probably the user would have also a phone number, okay? And he would probably would be nice to have the same phone number mapped to SIP.
Yes, this is what...
That's a political problem, probably.
This is what ENAM is doing, and that's why I was saying it's a layer 9 problem, because the regulation for domains is in charge of who is giving the domains. The regulation of the numbers is in the hand of the telecommunication operators. There's a big clash in between. And I still have to see a viable solution for this, but as long as your operator agrees to let you use your number on a SIP identity, then that's it. I think maybe it could be not really scalable because of the large number of users that then would like to move to SIP, but yeah, this is something also to test, to understand what are the limitations of such an implementation.
Right, thanks for the question, thanks for an answer, and thanks for advertising TFVVC so wildly. So thank you, Saverio. And we have come to our last presentation of this session. Last speaker is Petr Holub. Petr is from University of Masaryk. In the core, you will see that it's his PhD student, and as I heard, his PhD thesis were just finished last week. Petr is also involved in chestnut activities of grid, multimedia, and high-speed networking. And today, he's going to talk about ambiguous user-empowered networks of active elements. So I'll try to get your presentation.
If I may get the presentation. Can I be heard? Even with the microphone or just my voice?
No, we need microphone for streaming.
Okay. Okay, so good morning, ladies and gentlemen. What I'm going to talk about today are what we call ubiquitous user-empowered networks of active elements, which we are using for synchronous multimedia distribution and processing. Regarding outline of my talk today, I'll talk a little bit about architecture of active elements, about the design principles we are using, about separation of control plane and data plane. Okay, still doesn't work? Yep, sure. But it works, okay. At least here. About content organization, and then I'll follow with discussion of properties of such networks, so like scalability, robustness, and which is important topic of this conference, about pervasiveness or capability of the network of being ubiquitous. Okay. Okay. Oh, no problem. And I'll conclude with prototype implementation and discussion of its properties and then I'll conclude with some conclusion. So regarding the goals of our work, we targeted to provide a completely user-empowered solution for either video conferencing or any synchronous virtual collaboration. And our work was motivated primarily by experiences with multicast and its deployment problems, because you are always dependent on your network administrator, whether you have or you don't have the multicast. So we wanted to create an environment for which you don't need to beg your administrator to provide you with some service, but where you need your administrator just to run the basic unicast routing in your network, and you don't need anything else. And the unicast routing is just the very basic network service which should be provided in every network you have. Otherwise, you can fire the network administrator if he's not or she's not able to provide you unicast routing. So we also wanted to provide capability of traverse different firewalls and NATs, and we wanted to build several models with several distribution models with different scalability and robustness ratios. And we wanted to provide, of course, open and modular implementations, all the nifty things you want to have with your implementation. The design of active element stems from user-empowered reflector, which again follows from our research in router designs in active networks or networks of active routers. And we designed it in a modular and user-empowered way, and it's standalone central element which provides support for data distribution without multicast support, and it provides also processing capabilities like a gateway or synchronizer of two streams. It can work as a TCP tunnel. That's first thing which is useful for pervasiveness. And it also provides strong end-to-end security, which we lose, which is the only thing we currently lose in the networks of active elements. But the problem with the central reflector is it scales badly. It scales to the square of number of connected clients, which is definitely wrong. And of course, the robustness is not good, since it's a central element, and if that element drops out, then you lose your connection or your virtual collaborative environment. For the active elements and their networks, we have decided to separate control plane and data plane, meaning it's something similar to, for example, FTP transfer, which you have some control connection which needs to be as robust as possible, and some data connection which needs to be, first of all, as efficient as possible, and also it should be robust to some extent. But the separation is done because we have different requirements. The control plane must be robust, the data plane must be scalable and well-performing. This is the architecture of the active element from inside. So the lower part with network listeners, shared memory, and packet sender scheduler is the part of the data plane. So the data flows in through the network listeners, they are placed into the shared memory, and they might be processed by the processors, and finally they are sent to the receivers. The middle part, the messaging modules and kernel, are the internals of the active element. Basically, the messaging module is used for communicating with the kernel of the active element, for steering it. And the upper part is the part for management and information provisioning in the network of active elements. Okay, regarding the control plane, because robustness is the most important feature of the control plane, we have chosen a peer-to-peer network for building the control plane. The peer-to-peer networks are also nice in the fact that they are user-empowered. At least most of them are user-empowered, or almost all of them. They are usually not very efficient, but it's not a problem because only a control information is flowing through the control plane in the network. And also the scalability and the efficiency of the network can be improved to a large extent by deploying a super peer scenario, which can be characterized like, if you have read Orwell, all animals are equal, but some of them are more equal. So it works in the super peer network as well. Not all the peers are equal, because some of them are more equal. And this reintroduces hierarchy into the peer-to-peer network. And you might know that usually systems with some hierarchy are more efficient inherently. The control plane, the peer-to-peer network provides for us usually discovery service, so that if you run your own active element, you are able to connect to the network of other active elements which are in a surrounding. And it provides usually point-to-point channels for communication. Sometimes it provides also broadcasting or multicasting capability inside the control plane. Regarding the distribution models for the data plane, we have analyzed several models differing in scalability or efficiency and robustness ratio. Basically, we have studied two-dimensional full mesh networks, three-dimensional layered networks, which are both very robust, especially because there are no intermediate hops in the network, so any dropout of some active element in the network influences just the clients that are directly connected to that active element. So no complicated recovery is needed. And of course, we have analyzed spanning trees, which are much more scalable, but which need much more complicated reconstruction when some outage occurs. And we have also provided content organization, because such an active element network usually provides more than just a single content in a single format. So the content organization is in a tree-like hierarchy, with a content group, which might be some video conference, then content, which is, say, an audio stream or video stream from one client to all others, and then formats. Usually there can be more than one format in which each content is distributed. For instance, some clients might not support the high quality. I don't know if we are talking about high quality video conferencing. We might use, for example, DV over IP transmission. So not all the clients might be capable of receiving and processing DV stream with 30 megabits per second bandwidth. So we might run some transcoding gateway, which might be run on as a processor on some of the active elements in the network, and it transforms the original format into some new format, for instance H261 or 263, and tree-like hierarchy allows you to know which format is predecessor or successor of each format. Okay, now I'll proceed to the properties of networks of active elements. So basically, what we are interested in is scalability, first of all. Of course, the simple distribution models are not that efficient as spanning trees. We have analyzed two-dimensional full mesh and three-dimensional layered mesh models, and came up with analytical solution of a number of streams which are flowing through the network in each of these cases. And it turns out that the limiting is the number of outgoing to the standalone reflector, and you can see that it scales much better than the standalone reflector, simply because you don't have total number of clients squared, but you have number of clients per reflector squared times number of additional active elements for two-dimensional mesh, and it even improves for the three-dimensional layered mesh. Of course, the spanning trees are most scalable, and especially when it comes to minimum spanning tree. But for spanning tree, there is a problem with robustness because it needs to be rebuilt. So we have come up with an idea of having multiple spanning trees. That's why I'm not talking about minimum spanning tree, because we are not necessarily looking for the minimum spanning tree. We're looking for several spanning trees, so that you pre-build them, and if an outage comes, you can just switch to the backup trees you have prepared already. And latency of the switch is now not dependent on time to rebuild the multicast tree or the spanning tree, but is dependent only on speed of broadcast of the outage event inside the control plane of the active element network. Regarding pervasiveness of pervasiveness of the network, the control plane implemented as peer-to-peer network is usually pretty pervasive. There are usually means for peer-to-peer substrates how to penetrate both NATs and firewalls. And regarding the data plane, we support tunneling through TCP ports, or we support predefined ranges of UDP ports, if that's supported. And also we are thinking about wrapping content. For instance, if you have a firewall which does a deep packet inspection, it's not sufficient to tunnel your traffic through port HTTP through port 80, but you need to simulate that it's real HTTP traffic, so you can, for instance, use base 64 encoding and wrap it into the XML or HTML tags. So that it's hard to discover on using deep packet inspection. The prototype implementation is currently written using ANSYS-C. This is because we wanted to achieve maximum portability with minimum requirements on the underlying machine. For instance, there are quite a few machines which can't run Java virtual machines, so you need something even simpler. So we use ANSYS-C, and we have used Juxta-C for implementation of the control plane in a peer-to-peer way. Basically, we have encountered a problem with Juxta-C substrate or framework because the standard or the official implementation of Juxta is in Java, and the Java versions are always a little bit ahead of Juxta-C version. But they are quite usable when it comes to latest CVS versions. We have implemented the network management and network information service modules into the active element. The network management provides basically ID generation, provides message passing in a point-to-point way. It supports broadcasting to some extent, and it also supports network monitoring, which is important for robustness. And the network information service currently provides information about about content in the network and about round-trip times measured in the network, which is important for building as minimum spanning trees as possible. We plan to implement other measurements like bandwidth measurement or bandwidth estimation based on interpacket dispersion. Basically, this is view of how the network of active element might look like in a Juxta iView tool. And we are able to use the prototype implementation with multiple clients, starting from arranging from MBOM tools like VIC or RAD, through video LAN client VLC, through DV over IP or HDV over IP, to even our current or latest results from last week are even uncompressed HD video. So again, you might distribute even HD video using our framework. Basically, regarding our future work, we want to study additional robust and scalable data distribution schemes. We want to study a security model for the networks of active elements. And of course, we want to finish and polish up the implementation. As I mentioned a while ago, we found that we are able of duplicating more than 1.5 gigabits per second data streams, which is suitable for distribution of uncompressed HD video in multi-party uncompressed HD video conferencing or collaboration. And we want to also provide some interface, some nice user interface for non-geeks, for ordinary users. I'd like to acknowledge support by CESNET research project and one of our colleagues for helping with the implementation. Thank you for your attention, and if there are any questions.
Yes, questions, please.
I'll be more than happy to answer.
Yes, just wait for the microphone.
Thank you. Just curious, you mentioned that in order to provide pervasiveness of your solution, you're about to pack your data into base 64 and try to put them through HTTP traffic. So I was just curious about which MIME type are you going to use?
Actually, it doesn't matter. It's just that we need to pretend that it's a valid HTTP and some HTML traffic. So I don't care really, because it's just really just about pretending, not about being a real request response architecture.
I was just curious, in order to let our administrators to know how to stop the huge amount of data that's running.
Well, we might change it on fly, just to make sure that that they are unable to do it, or even to generate a new MIME types.
Right. Anyone else? Doesn't seem to be the case. And thanks, Peter. And thank you to all speakers again.
Okay.
We are a little bit early, but I hope you will not mind a little bit longer coffee break. I just wanted to remind about the evaluation forms, which are accessible online. And also, I think you can get a paper copy if you don't like the online idea. Oops, sorry. And just another reminder that there is TFVVC meeting indeed this afternoon. It will start at 1:30 in the room E, which is upstairs. If you haven't registered yet, then maybe you better talk with me, because there might be some complications. No food. Complications means no food. Thank you.